Hi, my name is Brent Dell. I'm a PhD student here in the Geospatial Information Science, working with Dr. May Wan. And today I'm going to briefly talk about our research, which is a space-time plume approach to clustering crime in Dallas, Texas. So overall, our research goal here is to present a novel clustering method that basically addresses some of the disadvantages and limitations of previous clustering methods. We're interested in the crime distribution across the city of Dallas, and we want to know the relationships in space-time of these crime event points. You can see a map here that I created showcasing the data set that we've received from the Dallas Police Department. And we have a 5-year data set from June 1st, 2014 to April 22nd, 2020, with over 400,000 events. So the traditional methods of clustering, such as hotspot analysis and space-time cube or emerging hotspot analysis, predominantly work by dividing the study set into set homogeneous shapes, like either a square for hotspot or a bin, like a three-dimensional cube for emerging hotspots or space-time cube. And there is some issues and limitations with that, where we may introduce some bias in how we divide the crime points in our data set. And these output results from these hotspot analysis may not necessarily show how the crime types have changed over time or how they relate, or and they may also be misleading. Like if you look at this map that I've created here using a hotspot analysis, this map may mislead viewers into thinking that the blue areas may have less crime and therefore may not be as interesting, but that may not necessarily be the case. Other density type clustering methods such as dbScan or ST-dbScan have kind of filled these or have tried to address some of those problems by being able to create clusters of varying shapes and not limited to predefined locations, but they also lack sensitivity to clusters of varying density. So if you imagine, you're looking at crime event points in an apartment complex, and you use a certain spatial parameter or distance measure to see if they have, a cluster there. That spatial distance parameter you select may not apply in a single family neighborhood where the houses are farther apart, whereas in the apartment complexes they're closer together. So our thought basically is that the underlying spatial structure of the buildings, the use type, is it a park, things like this will influence what distance parameter you should use when looking for neighbors surrounding you. And so our ST-plume algorithm, which stands for space-time plume, basically is founded on this idea of spatial structure and uses that to create a variable spatial epsilon or distance parameter, distance threshold, basically, to figure out if other points should be considered neighbors. And so that's kind of what's described here. We call it ST-plume because it kind of resembles a smoke cloud rising in the air, right? And so if you imagine, like, there's a fire and the smoke is rising, and it would take this interesting shape and it would rise over time and may shift and move. And that's kind of the general idea or concept that we're trying to convey here. We run our algorithm with a variety of temporal epsilons, and these temporal epsilons are basically time intervals. And so we say that, if it falls within this number of days, these points should be related in time. And so this is a variable kind of temporal epsilon here. You see that we've done some experiments from as little as 7 days all the way as large as 91 days, so basically 3 months. And the plume's outputs you can see here. You can see basically these shapes. And it's a little challenging to see here because these are inherently 3D clusters that I'm trying to display on a 2D image. So it's a little confusing. But the color ramp here basically signifies time, the z-axis. So the lighter colors at an earlier time, and then the darker colors are at a later start time. I showed the plumes here again at the bottom. This time they're kind of transparent with the actual events that make up that plume inside of them. And so you can see basically it's a convex hole surrounding all of the points that fell within the same plume. And I've color-coded them here, red for violent crime and purple for non-violent crime, to give you an idea kind of what's kind of happening over space and time in this location. And you might argue and say, like, well, hey, shouldn't these be all one plume? And I would agree, but there's actually slight gaps in between here. And like, for example, this was run in a 14-day temporal interval. And so the gaps between these were larger than 14 days, so therefore they were excluded. But now to relate these, we might actually look at linking them in time. So if we look at the next temporal interval step, for example, 21 days, and we see that these plumes have merged, then we might argue and say, hey, that they actually are related and we should consider them to be similar. And so that's kind of what you see going on here. All of these teal plumes effectively merged in a later time period, which is that gray polygon surrounding them. And so therefore I can come back and say that, hey, all of these teal plumes should be related. And so then we can start looking at how the crime plumes shift over time. How do they interact with each other? What does it say about predictions? So if I look at the crimes in this plume, do they basically predict what's happening in this plume, or is it completely different? So forth. And so basically, you can see we're basically creating new insights, new questions to be asked about how crime relates. And we're basically going beyond the traditional hotspot, our DB-scan style of grouping crimes together, and it's bringing out some exciting new questions and new research directions. So yeah, I want to thank you for your time. I mean, I can keep going on and on about this. It's pretty exciting for me, but yeah, I appreciate your interest. Thank you.